Good morning. Hi, I am Dr. Manoj Sahani. In the current scenario of COVID-19 outbreak, I request you all to take utmost care of yourself and your family members. On behalf of the PDPU family, I request you all to stay at home and be safe. In the previous lectures, we have discussed about the interpolation and extrapolation. We have also discussed about the interpolation methods for an equally and unequally spaced intervals. The interpolation methods that we have studied for an equally spaced intervals are Newton forward interpolation method, Newton backward interpolation method, central difference formula, and specifically if I state Stirling's formula. For an unequally spaced interval, the following methods are discussed: Lagrange interpolation method, and the second, Newton's divided difference formula. Now, using all of the above, we will study about, in this lecture, the numerical differentiation. Now, first of all, what is numerical differentiation? As you can see it here, numerical differentiation is the process by which we can find the derivative or derivatives of a function at some value of the independent variable when we are given a set of values of that function. If we desire to find the derivative of a function at a point near the beginning of a set of tabulated values, we use Newton-Grigori forward interpolation formula. If we desire to find the derivative of a function at a point near the end of a set of tabulated values, we use Newton-Grigori backward interpolation formula. To find the derivative at a point near the middle of the table, we should use a central difference formula. So, the above set of formulas are valid if the values of the arguments are equally spaced. In case, if the values of the argument are not equally spaced, we use either Lagrange interpolation formula or Newton's divided difference formula. So from above, we conclude that to each of the interpolation formula, we can derive a formula for finding the derivatives. So, brief introduction. As discussed before, let there be a prescribed n plus 1 pair of values, that is xi, yi, I is varying from 0 to n with a common difference 1, where x0 is less than x1, x1 is less than x2, and similarly it goes on up to xn. We assume that there exists some functional relationship between x and y. Let us say y is equal to f of x, and that the function f of x is differentiable in the closed interval x0 to xn. As the function is not known in general, we use numerical methods to approximate the first and higher order derivatives of y with respect to some independent variable, let that be x. So the derivatives can be represented as dy by dx. In short, we can also write it as y dash. Higher order derivatives, d square y by dx square can be written as y double dash, and dqy by dx cube can also be written as y triple dash. And similarly, other higher order derivatives can be calculated at some point x belonging in the closed interval x0 to xn, where x may be a tabular or non-tabular point, including the points x0 and xn. A tabular point means, that is, I am talking about the points x0, x1, x2, xn. Where non-tabular points, it can lie between x0 to x1, x1 to x2, or between xn minus 1 to xn. So in this, we'll be deriving the derivatives using the Newton forward interpolation formula. In my next lecture, I will be deriving the derivative using Newton backward interpolation formula. And in the lectures ahead, we'll be deriving derivatives using central difference formula, specifically Stirling's. So here we'll be deriving the derivative using Newton-Gregory interpolation formula. So suppose we are given the following values of y equal to f of x, a function, for a set of values xi equal to x naught plus ih. As we know that Newton interpolation formula is valid for an equally spaced intervals. So that is why xi is equal to x0 plus ih, where I is varying from 0 to n and h is the step size, where x naught is the first value of the interval. So as discussed in my previous lectures, the Newton interpolation formula is defined as yp is equal to y0 plus p delta of y naught plus p minus 1 by factorial 2 del square y naught plus p minus 1 p minus 2 by factorial 3 del cube y naught plus p minus 1 p minus 2 p minus 3 by factorial 4 del 4 y0 plus dot dot dot. I am putting this as equation 1. As we all know, delta, delta square, delta cube, delta 4 are the first, second, third and fourth order forward differences, whereas p is being defined as x minus x naught by h. As I mentioned before, h is the step size, x naught is the first value of that interval, which can also be written as x equal to x naught plus ph. So for an equally spaced interval, I mean that x1 minus x naught equal to x2 minus x1 equal to x3 minus x2 equal to xn minus 1. Now simplifying the equation 1, it can also be written as yp same y0 is same, plus p delta of y0 plus, if I expand it and remove the bracket, it can be written as p square minus p by factorial to del square y0. If I multiply all these three terms and expand it, it can be written as p cube minus 3p square plus 2p by factorial 3 del cube y0 plus, and if I multiply all these four, it can be written as p4 minus 6p cube plus 11p square minus 6p by factorial 4 del 4 y0 plus the series goes on, which I am naming it as equation number 2. Now very simple, that we'll be using it to find out the derivatives, which we call it as the chain rule. If I need to find out the derivative, first order derivative, so I'll be using the chain rule, which can also be written as dy by dp into dp by dx. So what is dp by dx? Now from, as you can see it here, this one, p equal to x minus x naught by h, which I have also mentioned it here, dp by dx is equal to 1 by h, as the derivative of x is 1, where x naught and h are constant, so its derivative is 0. So it is 1 by h minus 0, which is 1 by h. I hope that you have understood at this point. Now, as you can see, this is equation number 4. Now if I substitute equation number 4 in 3, I will be getting, as you can see it here, that is dy by dx is dy by dp into dp by dx, which is being mentioned in third. So it is 1 by h dy by dp. Now I need to calculate dy by dp now. Now to calculate dy by dp, I will be using equation number 2. So what does equation 2 says? I am putting it parallelly. So if I take a derivative of this second, here y0 is constant, so the derivative of the constant is 0. So I have put it as 0. Okay. Plus delta of y0 is constant, and the derivative of p is, that is 1. So I am moving out here the derivative of p with respect to p. Plus again in the next term, del square y0 by factorial 2 is constant, and taking the derivative, that is p square minus p from the equation number 2. Similarly, del q y0 by factorial 3 is constant, so it will be d over dp of p cube minus 3p square plus 2p plus the fourth term. So it will be del 4 y0 by factorial 4, as it is constant, so it is taken outside the derivative, and the derivative of the p4 minus 6p cube plus 11p square minus 6p, and similarly it goes on. So dy by dp, I am getting it as first term, as you can see it here, because the derivative of p with respect to p is 1, plus the derivative of p square minus p, so it is 2p minus 1 by 2, factorial 2 is 2, so it will be del square y0, plus the next term is p cube is 3p square, 3p square is 6p plus 2p, the derivative is 2, and factorial 3 is 6, and del cube y0 plus. The next term is del 4 y0 by factorial 4, that is 24, and the derivative of p4 is 4p cube minus 6p cube derivative, it is 18p square, 11p square derivative is 22p, minus 6p derivative is minus 6. So this equation number 6 give me dy by dp. Now if I substitute equation number 6 in equation number 5, I'll be getting the derivative dy by dx. So it is 1 by h, that is constant, and I need to put dy by dp from equation number 6. So I am substituting it here. So I'll be getting 1 by h del y0 plus 2p minus 1 by 2 del square y0 plus 3p square minus 6p plus 2 by 6 del cube y0 plus the fourth term. Now this equation number 7 is, if you see, is used to compute the first derivative using Newton forward interpolation formula. And as I stated in the beginning, that the Newton forward interpolation formula is used to find the values near the beginning of a set of our tabulated values. So the first derivative this equation number gives is being used to find out the derivative near the beginning of a set of tabulated values. Now if I substitute in this equation number 7 the value of p, so p is being defined as x minus x naught by h. Now if I replace this x with x naught, we'll be getting x naught minus x naught by h, and in that case p becomes 0. So if I put p equal to 0 in equation number 7, this equation number 7 reduces to equation number 8. So if you see it here, I am mentioning it here, the first order derivative dy by dx at the point x equal to x naught, where p becomes 0. So it is 1 by h delta of y0. If I put p equal to 0 here, it will be minus 1 by 2 del square y0. Similarly 0 0 in the third term, it will be 2 by 6, which is 1 by 3 del cube y0. And the fourth term, p equal to 0, this first three terms becomes 0, and it will be minus 6 by 24, which is minus 1 by 4 delta 4 y0. Okay, so equation number 8 will be used when x becomes x naught, and in that case p becomes 0. So using this concept, we'll be going to calculate a formula for the second order derivative. Now for the second order derivative, that is d squared y by dx square, it will be d over dx by d by dx. Now this dy by dx can also be written as 1 by h dy by dp, as we have seen from equation number 5. So this is equation number 5 that we have seen it. Okay, so this again I'll be using the chain rule for the second order derivative. So this d over dx can also be split into d over dp into dp by dx, which we call it as chain rule. And now this dp by dx we can write it as 1 by h. So 1 by h is there, 1 by h is here also, so it will be 1 over h square. And what is the remaining term? It will be d square y by dp square. So I am putting this is equation number 9. So we need to calculate now the second order derivative d square y by dp square. Now how do we calculate d square y by dp square, which can also be written as d over dp dy by dp? As we have already seen that dy by dp we have already calculated from equation number 6, as you can see it here. Okay, so this is equation number 6, and I'll be using this equation number 6 to calculate the second order derivative. So I am differentiating it again, equation number 6. So as you can see it here, I am putting it parallelly. So delta y0 is constant. So if you take the derivative of this, it will be 0. So I have put it as 0. Similarly, 2p minus 1 by 2 del square y0 by 2 is constant. If you take the derivative of 2p minus 1, you will be getting 2. And 2 over 2 is 1. So you will be getting del square y0. Similarly, for the third term, it will be del q y0 by 6. So it will be del q y0 by 6, and taking the derivative of 3p square minus 6p plus 2 with respect to p. And similarly for the fourth term, del square y0 by 24 is constant, taking the derivative of 4p cube minus 18p square plus 22p minus 6, which we have got from equation number 6. Okay, so here if you see, simplifying this term, it will be del square y0. Simplifying this 3p square minus 6, that will be 6p minus 6 divided by 6, you will be getting del q y0. And similarly, simplifying this, it will be 12p square minus 36p plus 22, as constant derivative is 0, and divided by 24. So it will be del 4 y0 and the leftover terms. Now substituting this equation number 10 in equation number 9, you will be getting the second order derivative, that is d square y by dx square. So 1 by h square is same, and d square y by dp square you will be getting from equation number 10. So now this equation number 11 is used to compute the second derivative near the beginning of a set of tabulated values. Again, using the specific case, let us suppose if x equal to x naught, then p becomes 0. Okay, now if p becomes 0 here, the second order derivative reduces to del square y0 is the same. Here if we put p equal to 0, it will be minus del q y0. Here these two terms become 0, it will be 22 by 24, which will be 11 by 12 del 4 y0, and the leftover terms. I hope up to this point it is clear to you. Now it's difficult to remember all this process, so I am giving you the shortcut for finding out the formulas for equation number 8 and 12 when p is 0. We have studied in our lecture the shift operator and its relation with the forward difference operator and a differential operator. So we have studied that capital E, which we call it as a shift operator, is equal to exponential raised to the power h. H is step size. D is a differential operator, which is equal to 1 plus delta forward difference operator. Now if you take this equation number 13 and taking log on both the sides of this equation, you will be getting HD is equal to log 1 plus delta, which can also be written as D equal to 1 by h log of 1 plus delta. So D is equal to 1 by h, and if you expand this series log 1 plus delta, very standard series, you will be getting delta minus delta squared by 2 plus delta cube by 3 minus delta 4 by 4, which you can see this is same as that of equation number 8 that we have derived it. Okay, similarly if you take equation number 14 and 2 times differentiate it or take a square of it, then you will be getting 1 by h square, and if you take the square of it, this the bracket term, you will be getting delta square minus delta cube plus 11 by 4 delta 4 minus similarly other terms, which you can see it's same as that of equation number 12. So these are the two shortcuts to remember it, and I hope that up to this point it is clear to you, and in our next lecture we'll be discussing about the numerical derivatives, the extension of it using Newton's backward interpolation formula as well as Stirling's formula, which is actually central difference formula. And I request you that in this a very serious situation across the world, be safe and stay at home. Thank you. We'll be meeting again soon. Thank you once again.